Imagine looking up at the night sky, the way humans have for hundreds of thousands of years, and thinking you understand the rules that govern it. Stars are born, they burn, and they die. Planets form from leftover dust and rock, swirling around in graceful obedience to the laws of physics. For centuries, we've refined these laws, tested them, written them into textbooks. They're the quiet scaffolding behind our understanding of the universe. They tell us why the moon circles Earth, why comets streak across the sky, why Jupiter is where it is and not somewhere else. The universe might be vast and mysterious, but at least the rules seem reliable. And then, we found it. A planet so strange, so out of place, that every page of our cosmic rulebook started to look like it might need rewriting. Astronomers gave it a catalog number that sounds sterile and bureaucratic, but the whispers in observatories carried more colorful nicknames. The Forbidden World, the Anomaly, the planet that shouldn't be. Its existence isn't just unusual, it's a problem. Because, according to everything we know about how planets form and where they can survive, this one shouldn't even be here. Not in this orbit, not with that composition, not around that kind of star. When you first hear about it, it almost sounds like science fiction, as if some alien civilization built a world and parked it in a place where nature would never have put it. Except, this is no fiction. This is a real planet, cataloged, measured, and confirmed by some of the most precise instruments humanity has ever built. To understand why this discovery is so unsettling, we have to remember that planets don't just pop into existence like magic tricks. Theories of planetary formation have been hammered into shape over decades, tested against our own solar system, refined with data from thousands of exoplanets discovered in recent years. These models tell us the right distances, the likely compositions, the dance of gravity and temperature and chemistry that decides what kind of world can exist where. Gas giants, for example, shouldn't sit scorchingly close to their stars unless something dragged them there later. Rocky planets shouldn't hold on to thick atmospheres if they're baked under relentless radiation. And small stars shouldn't have massive planets clinging to them in dangerously tight orbits without tearing them apart. But this planet, it breaks those rules, all of them. It orbits so close to its star that its year is shorter than some of our work weeks. Its mass and density make no sense for its environment. Theories suggest it should have either never formed there, or if it somehow did, it should have been destroyed eons ago. And yet, there it is. The first time light from it reached our telescopes, the reaction wasn't the pure thrill of discovery. It was confusion, followed by double checks, recalibrations, and more than a little denial. Scientists are used to surprises. That's the nature of exploration. But this wasn't just a surprise. It was a contradiction, a cosmic paradox wrapped in clouds and starlight. In a way, this planet reminds me of a kind of scientific ghost story. You think you know how reality works until you see something that, by all accounts, can't be there. And the most unnerving part? This isn't the only one. It might be the most dramatic example, but once we learned how to look, we found more impossible planets lurking out there. Our universe, it seems, has more imagination than our equations do. Before we try to explain the impossible, we need to go back, way back, to when our understanding of planets was shaped by a much smaller stage, our own solar system. For most of human history, planet meant Mercury, Venus, Earth, Mars, Jupiter, Saturn, the wanderers the ancients could see with the naked eye. We built our theories from what we could observe here at home. The neat arrangement of worlds around our sun looked like a natural template. Small, rocky planets close in, big gaseous ones farther out, everything moving in predictable, clockwork orbits. Then, in the mid-1990s, we started finding planets around other stars, and almost immediately, they shattered that neat picture. We found hot Jupiters, massive gas giants whipping around their stars in just days. We found planets with orbits so elongated they swing from scorching to freezing over the course of a single year. We found super-Earths, planets bigger than our own but smaller than Neptune, a size category that doesn't even exist in our solar system. Each discovery added wrinkles to our theories, but even with all these oddities, the rules still seem to hold in broad strokes. Planets close to their stars should be small and rocky, big ones should live farther out, and extreme cases, like hot Jupiters, could be explained by migration, the slow inward drift caused by gravitational interactions. Until this one. The planet that shouldn't exist doesn't just sit awkwardly on the edge of our models, it tears right through them, and that forces us into uncomfortable territory. Do we patch our theories, stretching them to cover this outlier? Or do we admit that maybe we've misunderstood something fundamental about how worlds are made? In the next stretch of our journey, we're going to unravel the physics of planetary birth, the cosmic recipe we thought was foolproof, and see exactly where this strange world refuses to fit. But first, take a moment to imagine it. A planet racing around its star, enduring conditions so extreme that every computer simulation says it should have been ripped apart long ago. And yet it survives, like a defiant reminder that the universe isn't obliged to follow our rules. To understand why astronomers are so rattled by this particular planet, we have to step into the story of how planets are born. Imagine a star being born in a dense cloud of gas and dust. It begins with gravity pulling material inward, squeezing and heating it until nuclear fusion ignites. The star is born in a burst of light, but the birth of the star is only half the story. Around it, leftover material keeps swirling, flattened into a rotating disk. This protoplanetary disk is the nursery of worlds. In this disk, the laws of physics, the ones we thought we knew so well, take charge. Tiny grains of dust collide and stick together. Over millions of years, they grow into pebbles, then boulders, then massive planetary embryos. Their fates are decided by location. In the warmer inner disk, volatile materials like water and methane can't condense. The heat vaporizes them, so planets born here are mostly rocky, like Earth or Mars. Farther out, beyond a magical boundary called the frost line, it's cold enough for ices to form. Here, growing planets can collect not just rock, but enormous amounts of ice and eventually gas, becoming giants like Jupiter or Saturn. This elegant picture has been reinforced by decades of observations, simulations, and, frankly, common sense. You don't expect an ice giant to be right next to the sun. It would have melted before it even finished forming. And you don't expect a small rocky world to be floating far out in the frozen dark. There's nothing for it to build from. And yet, our impossible planet sits right where the rules say it shouldn't. It's massive, far too massive for the thin scraps of material available so close to its star. By the time a planet that size could have formed naturally, the disk in that region should have been swept clean. That means it either formed farther out and somehow migrated inward, or it formed in place through a process we simply don't understand. Now, planetary migration isn't impossible. We know it happens. In fact, Jupiter itself may have migrated inward in the early solar system before gravitational interactions with Saturn shoved it back out. But migration leaves fingerprints, signs of disruption in the system, eccentric orbits, resonance patterns. This world doesn't have those. Its orbit is nearly circular, as if it's been quietly sitting there for billions of years. This is where things get uncomfortable. If it didn't migrate, then it had to form where it is. But forming there defies the physics of disk accretion. The building blocks just weren't there. Not enough solid material, not enough time. It's like finding a full-grown redwood tree in the middle of a desert that hasn't seen water in a century. Scientists have run simulation after simulation, tweaking parameters. Maybe the disk was unusually massive. Maybe the star formed in a dense cluster that funneled extra material inward. None of these tweaks produce a stable planet like the one we see. Every time, the models either fail to form it at all or tear it apart before the present day. What's worse, and more intriguing, is that this isn't a lone freak accident. In the last decade, our telescopes have uncovered a small but growing catalog of forbidden planets. Each one is different, but they share that same defiant placement. Too big, too close, too stable for their circumstances. They are like cracks in the wall of our theory, and the more we look, the more cracks we find. Some astronomers argue that our formation models are fine, that we just need to account for rare, extreme cases. Others believe these anomalies are the first hints of a deeper, more fundamental problem. Maybe the architecture of planetary systems is more chaotic than we thought. Maybe disk material can move in ways our equations don't yet capture. Or maybe, and this is the unsettling idea, our entire framework for how planets form needs to be rethought from the ground up. This kind of crisis isn't new in science. At the dawn of the 20th century, physicists thought they understood the laws of motion and light, until tiny discrepancies in Mercury's orbit and strange results in the lab forced them to invent relativity and quantum mechanics. Each time, the universe gave us a puzzle piece that didn't fit, and when we finally built a new picture, it was bigger and stranger than we could have imagined. This planet could be one of those pieces. But before we start rewriting the textbooks, we have to be absolutely sure we're not being fooled. That's why the next chapter of our story is about the detectives of astronomy, the instruments, techniques, and painstaking observations that confirmed this world is real. Because if there's one thing more unsettling than a planet that shouldn't exist, it's the possibility that it doesn't, that what we're seeing is an illusion, a trick of light, a mirage in the cosmic dust. And the way we found out is a story of patience, precision, and a little bit of luck. The discovery didn't happen in a single moment of cinematic revelation. There was no lone astronomer staring at a blinking light and whispering, "My God." Instead, it was slow, methodical, a gradual tightening of evidence until the conclusion became inescapable. But there was a first time, a flicker of data that hinted at something strange. It began with the transit method, a deceptively simple technique that has revolutionized our search for exoplanets. Imagine watching a star as steadily as possible, measuring its brightness down to the tiniest fraction. If a planet passes in front of that star from our point of view, it blocks a sliver of light. The star dims, just a little, and then brightens again as the planet moves on. The pattern repeats, like a cosmic heartbeat, telling us the planet's orbital period and even giving us a hint of its size. This is the same method that has given us thousands of exoplanet discoveries, thanks to telescopes like NASA's Kepler and TESS. The signal for this planet came during one of those long, patient surveys, just another star among hundreds of thousands being monitored. At first, it was easy to dismiss. The dips in light were deep, far deeper than expected for such a short orbital period. That suggested either a huge planet in an impossibly tight orbit or an error. Errors are common in astronomy. A passing asteroid, an instrumental glitch, even the subtle jitter of the spacecraft itself can mimic the telltale signs of a planet. So the team flagged it, ran the standard checks, and kept watching. The signal returned exactly when predicted. The dips were consistent in shape, depth, and timing. This was no random blip. Something massive really was whipping around that star every few days. That's when the second technique came in, radial velocity measurements. While the transit method shows us a planet's size, radial velocity reveals its mass by detecting the tiny wobble it causes in its star. As the planet orbits, its gravity tugs the star back and forth, shifting its light spectrum ever so slightly. Measuring this requires absurd precision, detecting changes in velocity as small as a few meters per second from dozens of light years away. The first radial velocity readings confirmed it. The planet was massive, far too massive for such a tight orbit. At this point, eyebrows in the research team began to climb. Something wasn't adding up. According to theory, there shouldn't have been enough solid material close to the star to build something this big. And if it had formed farther out and migrated inward, it should have been a distorted, unstable wreck. But it wasn't. The orbit was clean, circular, and steady. The numbers refused to budge towards something more comfortable. Each new observation only made the contradiction sharper. Behind the scenes, the scientific process kicked into high gear, and it wasn't always polite. There were long email threads debating whether the data could be contaminated by background stars, meetings where veteran astronomers argued over whether an unusual starspot pattern could be masquerading as a planet. One researcher even suggested that the star might have swallowed another planet in the past, altering its structure and skewing our measurements. But none of these explanations held up under scrutiny. The turning point came when a second, independent team, using a completely different telescope on the other side of the planet, detected the same transit pattern. They weren't looking for this particular star. They had been conducting their own survey. But when they found it, their measurements lined up perfectly with the original team's. Same period, same depth, same impossible conclusion. Now it wasn't just one group of astronomers with a weird result. It was two, working independently, in agreement down to the decimal. The impossible planet was real. Acceptance came slowly. Even as the discovery was prepared for publication, drafts were passed around with heavy caveats. If confirmed, possible alternative explanations. No one wanted to be the one who shouted "impossible planet," only to have it turn out to be a miscalculation. But the more people checked, the more the doubts evaporated. When the paper was finally published, the reaction in the astronomy community was a mix of fascination and discomfort. Here was a planet, hot enough to vaporize metal on its surface, massive enough to rival the largest gas giants, yet orbiting so close to its star that the standard formation models laughed in our faces. It wasn't just an oddball, it was a dare, a challenge from the universe, dropped right into our laps. Explain this. Some embraced it eagerly, diving into new simulations and hunting for similar cases. Others were wary, reminding everyone that the history of science is littered with anomalies that turned out to have mundane explanations. But in this case, the planet wasn't fading into statistical noise. It was right there, clear as day, every time we looked. And so the hunt began, not just to study this one world, but to figure out whether it was unique or the first of many. What followed was a wave of targeted searches, digging through telescope archives and peering deeper into the galaxy for more of these rule breakers. And the more we looked, the more unsettling the picture became. This wasn't an isolated fluke, which brings us to the truly uncomfortable part of the story, the part where we start seeing patterns in the chaos. Because if there are more of these planets out there, then maybe they're not exceptions at all. Maybe the rules we thought were universal aren't. Once the planet's reality was beyond doubt, the real chaos began. The theorists took over. And when theorists see something that breaks the rules, they react in one of two ways. Either they sharpen the rules until the thing fits, or they throw the rules out entirely. The first camp tried to fix the problem by tweaking the planet formation models we already had. One idea was in situ formation under extreme disk conditions. Maybe, they argued, this particular star's protoplanetary disk was unusually massive, dense, and short-lived. In such a scenario, enough solid material could, in theory, be funneled toward the inner region fast enough to build a planet of this size before the star's radiation cleared the disk away. But even the best-case simulations for this scenario only produced planets about half the observed mass, and most of those quickly fell into the star. Then there was the high-speed migration hypothesis. Maybe the planet did form farther out and then raced inward in a gravitational slingshot, pulled by interactions with other massive planets in the system. But this raised its own problem. Such a migration should leave the planet in a stretched, elliptical orbit. Yet our forbidden world's orbit is almost perfectly circular, more like a planet that's been sitting quietly in place for billions of years. Another theory tried to invoke stellar cannibalism. Maybe the star had swallowed another planet, or even a small brown dwarf long ago, spitting out debris that later recoalesced into this strange world. The problem? That kind of catastrophic event tends to destabilize the whole system, and there's no sign of such chaos in the star's surroundings. Some scientists went even more exotic. What if this isn't a normal planet at all, but the stripped core of a once much larger gas giant? In this scorched survivor scenario, the planet began life as a giant like Jupiter, migrated inward, and had its atmosphere blown away by the star's heat and radiation, leaving behind only the dense metallic core. That would explain its mass and density, but not its stubborn stability in that lethal orbit. And then there were the truly radical ideas, the ones whispered at conferences over coffee or scribbled on whiteboards with a sheepish smile. What if the laws of planetary formation are different in certain parts of the galaxy? What if something about the local interstellar environment, the density of the surrounding molecular cloud, the magnetic fields, the cosmic ray flux, can rewrite the script? We've always assumed our solar system was a pretty standard example, but what if it's not? One of the more philosophical proposals came from those who study emergent phenomena, the idea that complex systems can produce unexpected outcomes that can't be predicted from first principles alone. In that view, planetary systems are less like clockwork and more like weather patterns, deterministic in theory, but so sensitive to initial conditions that certain rare configurations are bound to appear, even if they look impossible to us. The forbidden planet, in this analogy, is like a perfect hexagonal storm on Saturn. It shouldn't persist, but it does. Of course, there's always the temptation to go further still. Some fringe voices, not in peer-reviewed papers, but in late-night panel discussions and online forums, have speculated about artificial origins. Could an advanced civilization have moved this planet into place? Could it be some sort of colossal engineered structure, a shell-hiding technology within? The evidence for such claims is non-existent. But the very fact that the planet is so improbable invites this kind of speculation. Humans are story-driven creatures, and when nature delivers a puzzle without an obvious answer, our minds leap to the dramatic. The debates have gotten heated at times. For every plausible hypothesis, someone can produce a stack of simulations showing why it doesn't work. For every careful explanation, another anomaly appears to undermine it. This is both frustrating and exhilarating for the scientists involved. Frustrating because it means years of work can be dismantled by a single new observation. Exhilarating because it means we're standing on the edge of something unknown, a gap in our understanding that could lead to a breakthrough. But there's an important thing to remember here. Science thrives on these moments. We don't advance by finding more of what we expect. We advance by being wrong, by finding things that don't fit, and then chasing them down until they do. And yet, while the research continues, the existence of the forbidden planet has already started to ripple outward into other fields. Astrobiologists wonder, if planets can form and survive in places we thought impossible, what does that mean for the potential for life? Cosmologists ask, if our formation rules are incomplete, how much else about planetary demographics might we be misjudging? And philosophers of science quietly smile, because they've been saying all along that our models are only as good as the data we feed them, and the universe doesn't care about our assumptions. The story of this planet is no longer just about one world. It's about a bigger question. How much of what we believe about the universe is really just a local truth, a pattern that happens to hold here but not everywhere? And that's where things get personal. Because once you start thinking about it, this isn't just a question about planets. It's a question about us. The strange thing about the forbidden planet is how quickly it stops feeling like a story about astronomy and starts feeling like a story about ourselves. At first glance, it's just a ball of rock or gas orbiting a distant star, something so remote it shouldn't matter to our daily lives. But the longer you think about it, the more it turns into a mirror, reflecting the way we understand the world, and more importantly, the way we change our minds. Humans are pattern-finding machines. We can't help it. It's how our brains are wired. From birth, we collect observations, connect dots, and build rules in our heads about how things work. Fire is hot, water flows downhill, friends are people who help you. These rules become the scaffolding of our mental model of reality. And most of the time, they work. They keep us alive, help us navigate the world, and let us predict what will happen next. But there's a hidden danger in this gift. Once a pattern feels solid, we start to trust it as if it's unshakable truth. That's exactly what happened with planetary formation theory. We looked at our solar system, saw its neat arrangement, and assumed it was the template for the entire galaxy. When the first hot Jupiter was found in the 1990s, it was a shock, but we adapted. We bent the theory, added planetary migration to the playbook, and moved on. The model survived. Then came this planet, and the bending wasn't enough. Now we're in the awkward space where the rules don't just need adjusting, they might need dismantling. And humans don't like dismantling things they've built, especially ideas. That resistance isn't just stubbornness, it's baked into us. Psychologists call it cognitive dissonance, the discomfort we feel when reality refuses to match our beliefs. The Forbidden Planet is a perfect example of cognitive dissonance on a cosmic scale. We can either cling to our old understanding and dismiss the anomaly as a fluke, or we can tear open our mental model and let something new take its place. Both options come with a cost. If you think about it, this is the same struggle we face in everyday life, just painted in starlight instead of streetlights. Maybe you believe a certain career path is stable until the industry collapses. Maybe you trust someone completely until they betray you. Maybe you think you know your own limits until you're forced to push beyond them. Every time, you're left with the same choice the astronomers face: defend the old map or redraw it. Science, at its best, is the art of redrawing maps without shame. It's a constant cycle of being wrong, adjusting, and being wrong again, each time a little less so. But scientists are still human. They feel the same pride in their work, the same hesitation to scrap something they've built over decades. And that's what makes this moment so fascinating. We're watching the scientific mind wrestle with its own nature in public view over a chunk of matter thousands of light years away. There's also something humbling here. For centuries, we've told ourselves that the laws of nature are universal, that gravity works the same in Andromeda as it does in your kitchen, that the chemistry of hydrogen doesn't change just because you've crossed a few billion kilometers. But the more we learn, the more we see how many of our laws are really just local customs of the universe. They work here, in this neighborhood, under these conditions. Step outside those conditions, and the customs change. Maybe that's the real lesson of the Forbidden Planet, that certainty is a luxury we can't afford if we want to keep discovering. The universe is not a fixed, tidy textbook. It's a restless, evolving conversation. And if we only listen for answers we already expect, we'll miss the most important things it has to say. And yet, even in our humility, there's awe. Because the fact that we can detect this planet, that we can measure the dimming of a star's light by a fraction of a percent across dozens of light years, means that whatever the rules are, we're smart enough to notice when they're being broken. That's no small thing. In that sense, the Forbidden Planet isn't just a problem to solve. It's a victory, proof that our curiosity can outpace our certainty, and that's worth holding on to. If you step back far enough, the story of the Forbidden Planet is the story of the universe reminding us that it's bigger, stranger, and more creative than we give it credit for. For all our charts, equations, and models, we are still in the early chapters of learning how reality works. We've mapped a fraction of our own galaxy, traced a few billion years of cosmic history, and already we're finding cracks in our explanations. Worlds that should have been impossible, yet orbit their stars as if to say, "Look harder." This planet, sitting in its tight, deadly orbit, is more than just a defiance of the frost line or a glitch in our simulations. It's a living example of science's greatest truth, that no theory is sacred and every truth is provisional. We don't know yet whether its existence will force us to rewrite planetary formation from scratch or just refine the edges, but we do know that we can't ignore it, and that's what makes it valuable. The human mind craves closure. We want the mystery solved, the last page turned, the answer underlined. But science rarely works that way. More often, each answer is a doorway into more questions, each solved puzzle revealing the next one waiting. The forbidden planet may one day be perfectly explained, its origin story charted in neat diagrams. And when that day comes, the real magic won't be in the explanation itself, but in the fact that we got to live in the space between, in the discomfort, the curiosity, the chasing of a truth we could sense but not yet hold. It's tempting to see this planet as a challenge to our authority over nature, a reminder that the cosmos doesn't bend to our rules. But there's another way to see it, as an invitation to keep asking, keep listening, keep looking into the dark for the flicker of something unexpected, because that's where the real discoveries live, in the gaps between what we think we know and what the universe is willing to show us. And maybe there's something deeply human about that. We too exist in places we shouldn't, surviving odds that history said were impossible, pushing into environments that should have broken us. The forbidden planet endures in its furnace orbit, and in its endurance, we can't help but see a reflection of our own persistence. One day, we may learn every detail about this world. We'll know whether it's the survivor of some ancient cataclysm, the product of conditions we never thought to model, or the first hint of a galactic pattern hiding in plain sight. But when we do, I hope we don't forget the way it made us feel now, small, astonished, humbled, and yet lit with the thrill of being wrong in the most beautiful way possible. Because that's the secret the universe has been telling us all along. The laws of nature are not cages, they're clues. And every time we find a planet that shouldn't exist, it's the cosmos quietly whispering, "Keep going."